Yes, I see. Of course, stop working. Great.
Can I see the presentation on the screen here? Yeah, thank you.
Wait. It's not fine PowerPoint. Close. You want this view here?
Yeah, I just need
This one?
Yeah,
Something. But it's funny because if I do that, it doesn't show there as well. So let's keep like this. It's fine. Should be clear. Zoom again. Oh, and then wait, just a second.
Let me know when you want to start, and I will start.
Okay. Now it's fine.
Are we ready?
Yeah, start it.
Okay, so welcome everyone. Andrea is going to talk about Dalorex, data local program execution and architecture for memory-bound applications. Andrea is a last semester bachelor student studying at a computer science department at the TH Zurich, and I think he's going to deliver an excellent talk. Good luck, Andrea.
Thank you very much. Okay, so hello everyone. Today I'm going to present you Dalorex. Dalorex is a data local program execution and architecture for memory-bound applications. This work is a work from the research team from the Department of Computer Sciences in Princeton University and was presented this very year at HPCA 29. So I'm going to start the presentation giving you a very short executive summary. So there is a problem that the research team identified. Mainly, it is that graph-sparse linear algebra workloads do suffer from memory bottlenecks and have also for memory co-utilizations, and other processing memory approaches do overcome these bandwidth limitations, but also do fail to achieve high co-utilization and do not have a strong scaling. So the goal is to find a new computer architecture design to overcome these kind of limitations by minimizing data movement, also improving work balance and resource utilization, and then also to avoid serializing features and be efficient. The observation that was made is that there is much room for improvement on prior processing memory approach tesseract. So the key ideas are to exploit new concepts like the FinFET SRAM tile-based distributed memory architecture, a task-based programming model, and also a processing unit co-located with the data. The final results are that Dalorex does improve both performance by 221 and energy consumption by 325 over Tesseract, and does also achieve strong scaling with over 16,000 processing tiles. So this is the presentation outline. I'm going to start with a paper summary, then will come my personal analysis of the Dalorex work, and at the end there will be some discussion. Starting with the paper summary, I'm going to give you some background and motivation to understand the work better. Then I'll present you also some previous approaches, previous works in this field, and also then comes the core of the presentation, that is Dalorex, with the evaluation methodology and strategy that the research team decided to use, and then the results and conclusions. So, starting with the background and motivation, graph processing algorithms are used in various fields like bioinformatics, natural language processing, also image processing and machine learning. All these fields are characterized by having huge data sets. For example, they might have graphs with millions of nodes and even billions of edges. So, for example, there is Wikipedia, the English version of it in 2018 had 13 millions of nodes and 163 millions of edges. Having these kind of huge data sets is going to provoke having memory bottlenecks when you're trying to execute some kind of algorithm. So one way to represent, obviously, these graphs in memory is going to use adjacent matrices, but these kind of matrices are going to be very sparse because they mostly contain zeros. So one way to compress them is to use the compressed parse row format. For example, in this figure, you can quickly see how you can compress a small matrix in just a few arrays by storing just the non-null values. And then you can either decide to store the indices of these values, or you can simply store how many values are in some row. For example, in the array dedicated to the row, you can see that the difference between the first two values, so the 2 and the 0, is going to be 2, is simply going to be the number of values that are inside the very first row of our matrix, and so on. So again, for some background and motivation, this is the pseudocode for the single source shortest path algorithm. As you can see in these points, we are accessing memory. And when we are doing it, for example, in the first part, we are accessing the current node. We want to do some computation on, and then later we are accessing its neighbors. And its neighbors are usually not going to be close to the current node. They might be very far apart. And what does this mean is that we are going to have many irregular memory accesses, and these are going to provoke having many cache misses. Moreover, when you're trying to parallelize this kind of algorithms in the classical manner, you are going to have different processing units that are doing some works. And then after some time, they need to communicate with each other to have the same site of memory. It has to be consistent. So there are these two places, the centralized frontier and the new frontier, where you're simply going to have some communications within processing units to have this kind of consistent site of memory. But this kind of communication do come with some costs. So presenting some previous works, there are hardware techniques like some general purpose cores with decoupling and prefetching like Pipette, or also RapAttack. And also there are other works that are accelerators that do pipeline the different stages of the graph processing. These approaches are very effective in hiding latency and increasing load balancing. But what they are not good for is that they are highly energy inefficient due to excessive data movement, and also they are limited by DRAM bandwidth. Some other hardware technique is actually to process in memory. One example is Tesseract from 2015. It does use the hybrid memory cube technology that is from 2011. This approach does achieve higher memory bandwidth by processing data near DRAM, but being vertex-based, having a vertex-based data distribution, this is going to cause load imbalance. Moreover, there are some remote calls that are interrupting and do incur in 50 cycle penalties. And having an hybrid memory cube technology, this kind of architecture is going to be constraining the number of cores that we are using inside the cube. So it's very difficult to make them scale well. Some software techniques are GRAPh-UC, that is a barrierless synchronous parallel model. This is very good for reducing the messages staleness and also to remove global synchronization barriers, but is not optimized for data locality and comes with high communication costs. So overall, the remaining challenges that we have are to achieve a good utilization of the computing resources to improve both performance and energy. Then also we are trying to overcome the irregular memory accesses and also to mitigate these communication costs. So right now I'm going to present you the Dalorex model, starting with the programming model, then comes the data placement, the hardware, and the network on chip. So this is the same image as before, the pseudocode of the single source shortest path. The goal of Dalorex is to split this kind of codes in different parts. These parts are called tasks, and they are doing so in each pointer in direction. The goal is to have each task simply to compute over the same kind of local data. For example, in here, in these points, you can see the pointer in directions, and then you can see how the code is going to be split in 3 different tasks. For example, the very first task is simply going to extract the current node information from the data. Then we compute the new distances to all the neighbors. And then at the end, we are checking if the computed distance is smaller than the previously stored value. But as I told you before, when you are trying to do some parallelization, you are going to have some communication costs. And since Dalorex does use this data local execution model, where each task is going to perform on the same data, you only are going to need some local frontier and not a global frontier as before. This does imply that you are going to use an additional task. In this case, it's going to be the task 4. And this task is going to be responsible for re-exploring the local frontier and does allow for a continuous execution flow of the tasks. So presenting you the hardware. These are all the components of the hardware: a task scheduling unit, the memory that is based in SRAM scratchpad, the processing unit, and the routing system together with the network on chip. So starting with the scheduling unit, with task scheduling unit, it is the most important part of Dalorex hardware. It is, let's say, the brain, because it does decide which task is going to be performed on the processing unit. Then presenting you the memory system, we have the SRAM scratchpad. I'm going simply to introduce you to the data placement strategy that Dalorex does use in the memory. So they do have a pipette-based SRAM scratchpad. This is a very new technology of SRAM scratchpad that does allow you to have very high densities of memory. For example, they do have 29.2 megabits each square millimeter in 7 nanometers. It is also characterized by having low latency and also a dedicated access. In the SRAM scratchpad, you are going to store your data arrays in compressed parse row format in 4 arrays. You are also going to store all the results of the tasks in the queues. And also you're going to store the actual code of the task in this task code location. The data that you are going to distribute across the processing units are going to be homogeneous and also randomized across all the processing units. This is a very good advantage because you are then going to have a very homogeneous way of distribute the data. For example, when you consider the hot nodes, each processing unit is going to receive the same amount of hot nodes roughly. So each processing unit is going to receive the same amount of computational work to do. So going on with the processing unit, it is located close to the memory and also close to the task scheduling unit, because it's in here that we are going to make our computations. And at the end, we do have the routing system together with the network on chip to simply communicate with other processing units to share results and so on. Dalorex does need an host system to initially feed the code and data inside the chip, and the chip design can have several processing tiles up to 128 by 128. So Dalorex, for the Dalorex network, Dalorex does not use a simple two-dimensional mesh network. This is a design that is very cheap, but comes with possible contention sources. Instead, Dalorex is going to use a torus network. This kind of network does not have contention sources. It comes with fewer hops and more resection bandwidth. A takedown for the torus network is that it is very bad for scaling. So when you're going to quadruple the number of tiles that you have in your chip, you are only going to double the dissection bandwidth. So one way to solve this issue is to use a mix of torus and rush network. This is going to be very good for scaling, and with a torus factor, with a rush factor of R, you are going to achieve a dissection bandwidth factor of R-1. So going on with the evaluation methodology, the research team decided to start from the tesseract processing memory approach and build up the evaluation method, adding at each step some optimization and reaching finally the Dalorex work. So I'm going to present you these optimizations. These are all the evaluation steps that they decided to consider. And for the very first one, they decided to add some very large caches to simulate the use of SRAM. Then they decided to test the optimization given by the array chunking and task splitting model that I presented you before. Then they decided to add a very basic task scheduling unit to test the fact that Dalorex is not going to be blocking and is not going to have any interrupting communication. Then comes also a uniform distributed model that has a better data placement strategy. Then there is also the traffic aware model that has the panel task scheduling unit, the more optimized one. And at the end, we are going to have the torus network on chip network improvement. So instead of using the simple mesh network, you're going to use the torus one. And then you're going to have the full Dalorex evaluation model with the torus and rush network. So as you can see, these are all the graph algorithms that they decided to test. We have BFS, we have single source shortest path, we do have weakly connected components, and also PageRank. They also decided to test a sparse matrix algorithm, simply because Dalorex can work on any kind of algorithm that does use sparse matrices. And these are also the data sets. As you can see, there are Amazon, Wikipedia, LiveJournal, and random matrices. And they do come with this number of vertices and number of edges. So for the results, here are the results for the performance. As you can see, the most present one is the data local result that is 6.2 over tesseract. And this is sign of having a very good data placement strategy by Dalorex. And also the second best one is the use of a basic task scheduling unit. This is more going to highlight how the tesseract processing memory approach does have some issues with the communications, because are going to have some interruptions that will incur in 50 cycle penalties, as I told you before. Overall, we do achieve 221 performance improvement over tesseract. It is not very clear if, by these results, if having a torus rush network on chip is actually very more performant than having a simple torus network on chip. So we need to simply have more data, more results to have this conclusion. So for the energy results, we do have huge results. The most present one is comes from the use of SRAM. This is 16 times over tesseract. As you can see, the tesseract LC column, that is the orange one, is much higher than the tesseract column that you can barely see. And overall, we do have 325 energy improvement over the tesseract work. From these results, you can actually see that using a torus network instead of a mesh one, you are going to spend more energy. It is roughly amount the 12% of more energy. This is obviously not a good thing, but if you remember the performance improvement of the previous slide, you can just say that it is an acceptable trade-off to have. Moving on with the throughput results. These are the throughput results. As you can see, when you are going to scale the size of your computations, you're simply going to be able to compute everything everything. For example, the very last configuration is going to, in this graph, it does have 16,000 tiles. This is a chip of 128 by 128. It does have a throughput of 2 tera operations per second and does use 10 terabytes per second of memory bandwidth, while the available one is 131 terabytes per second. Having this memory bandwidth not being saturated does allow the processing unit to process the vertices and edges at very high rates. Moving on with some results for the scaling. We do have the performance scaling results. For example, in this figure, you can see how Dalorex does achieve linear scaling until reaching the parallelization limits. These limits do come at circa 1,000 vertices per tile, and then the performance is going to be limited by the tiles, the processing units that are going to start for work. These are the energy scaling results. As you can see, with higher parallelization efficiency, we are going to decrease the energy consumption. Then we meet a deflection point at circa 10,000 vertices per tile. And then at the end, because of leakage energy, we're going to increase the energy consumption. So at the end, the conclusions are that Dalorex does improve both performance by 221 and energy consumption by 325 over the tesseract work, and does achieve very strong scaling with over 16,000 processing tiles. So now I'm going to present you my personal analysis of the work, starting with some strengths, then come the weaknesses, and at the end, some takeaways. So one good strength of this work is that it is the very first work that does use this FinFET-based SRAM for the design of a graph accelerator. This FinFET-based SRAM does allow you to simply pack more transistors than ever in memory. Then also the great performance and energy results over the Tesseract processing memory approach. These results are simply huge over Tesseract. And then there is also this very comprehensive and evaluation methodology of each single optimization. That is very interesting because allow you to have a lot of details for all the contribution that each component is going to give you. For the weaknesses, this paper does present a mix of already existing well-known ideas. For example, we do have a task model and also a data placement strategy that is very similar to a precedent work that is called GraphH. This is a work from 2018. Also, the Torus network on chip. It is not a new technology. It was well known before. For example, I found this paper from 2005 that does already test this network on chip. So Dalorex does not introduce any new concept. Moreover, they are doing some wrong claims. They are saying that Tesseract, that is a work from 2015, it is state of the art, but this is very not the case. And it is very easy to achieve great performance when you're comparing to a relatively old architecture. They could have compared themselves with GraphQ, that is a work from 2019, but they decided not to do that because they simply couldn't reach the same results as the GraphQ paper. But if they decided not to compare themselves with GraphQ, they could at least compare themselves with GraphP, that is a work from 2018. And this work already had speed up and energy saving compared to Tesseract by still using the DRAM technology and not SRAM technology. So there are missing comparisons with more recent works. Then another point is that Dalorex does focus on push-based algorithms and does not test any pull-based algorithms. So as the name says, when you're using a push-based algorithm, your computational units are going to push their results away to the other nodes. And when you're using a pull-based algorithm, you're doing the inverse thing. And they simply decided not to test them because they thought Dalorex could have used them. But what actually we can think about is that we have to remodel the whole programming model of Dalorex, because as I explained to you, the tasks are going to produce some results, and these results are going to be routed to other tiles. So you are going to simply redesign the whole programming model if you want to require some results from other processing units and make them come to your tile, to your processing unit. There is also some vagueness, and they are doing some unreasoned assumption. For example, in this case, they assume the energy of moving a flit at the router to be similar to an ALU operation. I'm going to explain you what a flit is. It is simply the result of a task execution. They are doing so without saying why is that, and they are not saying which ALU operation they are talking about. So this is definitely a weakness point. So my final takeaways are that Dalorex does massively parallelize applications that are memory bottlenecked and does exhibit strong scaling. Moreover, Dalorex reaches parallelization limits through the use of an uniform work balance, a task-based programming model, a traffic-aware TSU, and also a high bisection bandwidth network on chip. And this hardware-software co-design system is much more performant than what each single evaluated sub-design could have achieved alone. So now it's time for some discussion. I prepared some slides and hopefully you can either participate or not. So Dalorex does solve the issue of being memory bottleneck for some kind of workload and does scale well. So I'm going to ask you, what is the next problem? So after having solved the memory bottleneck problem, what does come next and how do you solve it? You don't have any idea? It is something that I already suggested you in the presentation, some slide before. So I'm going on. Simply, you could focus. I told you that Dalorex does reach the parallelization limits. So your focus is going to be put on these parallelization methods. You're going to try to find the best one. And for example, this work that is called graph pools, try to focus more on finding a better way to parallelize these kind of algorithms to simply achieve better performance. The next question is going to be, how could it be possible to use Dalorex on workloads that are made of trillions of edges? So the Dalorex chips that I presented you can work on graphs made of billions, a few billions of edges, I believe. So what does happen when you have simply a much larger graph? What do you think you can do?
There's actually one class in Zoom chat. Gerald or Mason,
Okay.
could you? I can read it.
Okay.
So determine which part of an application are data intensive and which not to do good task scheduling.
I didn't get the question.
Yeah, maybe. I also.
Do you hear me?
Yeah.
Maybe it is an idea regarding your previous discussion point that you were asking what else can be done to further improve. Yeah. So the student confirms that this was about the last question you had. Previous slide.
Okay. Yeah, I didn't get it.
So you asked in the previous slide, okay, what else can be done to improve performance? And the student is suggesting finding a way to determine which parts of an application are data intensive and which not, so that you can do a task scheduling. So not all parts of the application might benefit from these approaches. So the student is suggesting some sort of, let's say, partitioning based on that.
Okay, so I wasn't thinking about it. I don't know if it's possible on Dalorex, because Dalorex does use this programming model that is very based on splitting the code in different tasks, and these tasks do work on some local data. So I don't know if this idea is actually suitable for the question, but I might be wrong because I didn't get it completely.
So when the partitioning happened between different compute elements in Dalorex, can the, let's say, execution model be extended so it is partitioned between, let's say, Dalorex modules and some other host system, let's say, that would work better for, I don't know, non-data intensive parts of the application?
Yeah, I think you can obviously do this, but when you're executing these graph algorithms, you just have the computation of the graph algorithm is going to be split in these tasks. So you're not going to have other computations to do other than the ones of the tasks. So I don't know which part of the algorithm you could take away to compute on a different part of a possible system. Anyway, I'm going to move on to the next question that I already told you about. Are there any ideas about it? So what you can do is actually to simply tell the host system to use more Dalorex chips and then subdivide the graphs to these various chips. And another approach can be to use a very similar computer architecture design and then exploit the Dalorex software programming model. So, for example, you can use this Cerebras WSE chip, for example, that is very similar to the Dalorex chip description. This does have different processing units. It does use SRAM memory, and you can simply feed this chip the programming model of Dalorex, and it is going to produce you the result. And yeah, this chip, I believe it does have 40 gigabytes of memory inside the chip. So it can be suited for this kind of workload. So moving on, here there are some heat maps of two types of Dalorex architectures with different network on chips. I'm going to ask you simply what does characterize them and what kind of network on chip they might have, in your opinion. Do you have any idea? Is there something on Zoom, maybe? Okay, so as you can see, the first figure, the one above, does have the color is more homogeneous in the two images, while the one in the bottom, you have some more router utilization, for example, in the middle of this chip, and also you have more processing unit utilization at the very edges of the chip. So you can deduce that the one above is going to have a torus network on chip. This does allow you not to have any contention inside the network, so everything is more distributed, let's say. If you have to send a result of a computation from a processing tile to another processing tile, you don't have to pass in the middle of the chip, let's say, because there is no actual middle of the chip. You can simply find another route. And the one below is the mesh one, is the one that is less performing. As you can see, for example, in the image to the left, at the borders, you are going to have more processing unit utilization. And this is simply because the tiles, the processing unit at the borders, do not have as many neighboring tiles as the one in the middle, and so on. Okay, so this is the very last question that I prepared for you. I'm going to ask you what other kind of trade-offs do torus and Rouge network have. So I already told you about the energy when I showed you that you are going to use 12% more energy when you are using these torus and torus Rouge network instead of using the much simpler mesh one. Do you know what other kind of trade-off this network on chip might have, or no idea? Okay, someone was saying something, or?
I thought complexity might also be an important trade-off, since we were dealing with two different memory architectures. I think the Rush network is likely to be a bit more complex, right?
Yeah. In which sense do you mean is going to be more complex?
Like you said that the memory architecture that's used for Dalorex is actually a combination of two memory architectures. So that's why I meant the complexity is one of the aspects that's also need to be taken into consideration when it comes to the design of this memory.
Well, the Dalorex architecture is what do you mean with Dalorex memory architecture? The two ways. The two components of Dalorex memory architecture.
Wasn't it a combination of Torus and Rush?
Yeah. This is for the network on the chip. Yeah, it's not for the memory. Okay. Yeah, you do have this mix of having a Torus network and also a Rush network. So you're going to simply enable some processing tile to have direct communications with other tiles that are more far away from your current one. So some other trade-off that you might have are regarding the total for the area that you are going to use for applying these kind of networks. Obviously, if you are going to use a more complex, let's say, network on chip, you are going to use more area inside the chip. In the case of Torus, you do have a 0.2 total chip more area. And in the case of Torus Rush network, you're going to have 1.2% of total more chip area. These trade-offs, these costs are all justified by the huge performance improvement that you can see in this image, in this picture. You can also see how having a Torus or Torus Rush network on chip is not changing in the very first three workloads, but then it does change something. In this case, it's because the very last workload, random matrices 26, is simply is run on a 64 by 64 processing unit on 64 by 64 chip, while the rest is going to simply run on a 16 by 16 chip. So what I wanted to say is that these kind of improvements, the difference between having a Torus instead of having a Torus Rush, are visible only on larger chips and not on the smallest one. So now it's time for some questions. You can tell me anything. If you didn't get something, I can try to explain you better. Or if you have some, maybe if you want to have some more insights for Dalorex, you can ask me about it. Or anything else.
Yeah, if no one else has any comment, I would like to make a comment. Basically, thanks for the presentation, Andrea. So basically, I think this work, as we discussed as well in our meetings, has this interesting contribution with a large FinFET-based SRAM scratch pads, right? That enable just putting lots of data next to the processing unit. But I think that we discussed like the comparison points maybe do bad justice to the idea, because they should maybe compare against more relevant works and see how this FinFET-based technology can also help other sorts of accelerators rather than designing a new one, right? Overall, I believe also this topic of accelerating workload in the context of graph mining, bulk synchronous parallel graph algorithms becomes a lot more challenging these days with irregular access patterns and big data sets. And the applications also become a lot more demanding. For example, graph neural networks, which operates on large amounts of data, right? And new solutions are really important in this context to understand what we can do both at the memory side, at the compute side, how we can increase parallelization. So there are multiple research directions you can follow to tackle the performance issues in these workloads. Yeah, that's my take on this.
Okay, thank you very much. Are there any other questions? Okay, then I believe I'm done with my presentation. So thank you very much and have a great evening.